Okay, let's move on. And then now we would like to move on to uncertainty propagation. So how uncertainty propagates as you have a little more complicated system, because your system is not just a single element, single measurement, or single reading. It has multiple components in there, and they all interact with each other, and probably you're just measuring small portions of here and there. And let's think about this KUKA robot. And the important thing is you want to know the coordinate or the location or speed, whatever, at this point, right? But oftentimes they have some sensors at different locations, like here and there. And let's think about a case where we're trying to find the angle of this final position, like this angle. There's one angle sensor here and there, and they are measuring from this point, and they're measuring from that point. That's you. And we would like to find the uncertainty of theta, which is theta 1 plus theta 2. And theta 1 was obtained like that, and theta 2 was obtained like this. First, is there anything wrong here? Yes. It has to be what? 0.0, right? Good. Given this, we would like to find the uncertainty. And one way we can try is we can find the minimum value of this guy. And the case where we can have it as the minimum value is theta 1 is 19.5 and theta 2 is 14, because it says this measurement, it's plus or minus 0.5, so the min value for that is this. For this guy, the minimum value is 14. So the overall minimum value we can have is 33.5. And similarly, the max value we can have is 20.5 plus, and here it's 16, so we have 36.5 degree. So the total theta, the uncertainty of that can be what? Summation of these two, so 35 plus minus, how much does it change? It changes 1.5 and 1.5, so it's 1.5 degree moving up and down, right? And of course we would like to have it like that. And of course this is 20 plus 15, and interestingly you're just adding the uncertainties you had for individual values, right? And so we can easily know that our uncertainty of individual variables propagates and or increases. Anyone doing like woodworking or working in construction area, like part-time? No. You can easily maybe think about this thing. You're trying to build a very long, bridge, and you have small elements. Well, they are not small actually, but you have all of these within the spec. And then you're adding all those, and eventually, they're not aligned. The small uncertainty you had in there, or the tolerance, they all add up and they all propagate, and eventually these kind of disaster may happen. So that's something we would like to understand from this uncertainty propagation. Okay? All right. Any questions up to here?
I've got a question.
Yes.
So when you're solving for the theta, did you just add 20 and 15?
Mm-hmm.
Did you add the...
So we just wanted to find out what would be the minimum case we can have with this guy, right? And then obviously it's these two cases you add up, right?
Right.
And this is the max we can have for given variable. And then from here we can see that it's centered around 35 and plus and minus 1.5, the range we get.
Okay.
And so this is actually just the sum of these two,
Oh, okay.
and this value is coming from the sum of these two. Okay? So
Yeah.
that was the meaning of here.
Okay.
Good point. On the other hand, unfortunately, it's not this simple, and that's coming down here. Let's consider a variable, let's call it y, okay? And this is computed from a set of individually measured variables, and let's call them x of i's. Your y is a combination of these x's, x1, x2, up to x of n, and if that's the case, the combined uncertainty, delta y, for example, the combined uncertainty in this case was delta theta. So the total combined uncertainty is going to be defined as this. I is starting 1 up to the number of variables, and you're doing the partial derivatives times the individual uncertainty. So this x of I is the individual measurement, and we will need to know how to use this thing and calculate stuffs. Back to the example we just tried here. Theta is the combined variable of these two individual variables, theta 1 and theta 2. And the function that combines these two was theta 1 plus theta 2. So we have two variables, and the relationship between these two variables was that function, and that's just adding those two in this case. From here, this combined uncertainty theta, what we have to do is get the partial derivative of your f times the uncertainty of the first variable plus the partial derivative with respect to the second variable times the second variable uncertainty. And this is what? Theta 1 over theta, partial theta 1 plus theta 2. Because your function f is theta 1 plus theta 2. And don't forget that theta 1 plus theta 2. Then here comes the very challenging part. This value you need to find out. What's the value of this? Theta 1 plus theta 2, and you're trying to find a partial derivative with respect to theta 1. What's this here? Theta 2? This is 1. Do you remember? Like that? If you're doing a partial derivative, you are considering all the other variables except your x as a constant. So these are just constant, like you can consider this like 2. And x plus 2, you find a derivative with respect to x. That's just 1, isn't it? So this is 1, and we still have this guy. The value of that guy was what? It was 0.5. So it's 0.5 plus this one. What's the value of this partial derivative? 1, thank you. Because here, it's with respect to theta 2. So this guy, we're just considering as a constant, like 55. So this guy goes away, right? And we're multiplying that delta theta 2, which was this value. So 1. Therefore, it gives us 0.5 plus 1, so it is 1.5. Okay? We just got that value up here, 1.5, which was 1 plus 0.5, and that guy was obtained following this equation. let's try another one. Let's assume we had W and H, and this is for a rectangle. We have W and we have H, and we're trying to find the area here. And let's say W was 2 plus minus 0.1, or 20 plus minus 0.1. Well, I need to be more specific, like correct, like that. And let's say H was 10.0 plus minus 0.2. So if that's the case, we would like to find what is delta A, or the uncertainty of the area. Then what we do is we're just applying the same thing we just tried here. So let me just erase this to find some space. And delta A is delta W delta F times W plus, we have the second variable like that, times delta H. And what's this function, F? What was that?
W times.
Yes, correct. The area is obtained as W times H, right? So the function here shows the relationship between W and H to obtain this A, which is just multiplying those two. Okay, so if we write this thing one more time, this is del W times H, and times del W. Sorry, let's just move it down there. Plus del H del WH times del H. And this guy is what? Let's try one by one. What would be this? What was that?
H.
Yes, this is going to be H. It's same as, let me write this thing up here, del WH. This guy is same as something like del W times 2. H is going to be considered as a constant. These are only the variables. So, you know, this is going to be just 2, right? Just like that. Here we have the constant coming down there, okay? And this guy just comes down here, delta W plus this one is going to be what?
W.
W, and then we have delta H. So you can plug in these numbers to do a little bit of math and find the value there. H is 10, delta W is 0.1, W is 20, and delta H is this. So we can find whatever certain value there. And that's going to be what? The uncertainty of the total area. Okay? Any questions up to here? Okay, so then let's move on. And there are two types of definitions we have here, again, and maximum possible error and most probable error. And this is Y ABS, and the way you obtain this guy is and Y RSS. So these equations are all coming from the textbook, so you guys can later take a look at the equations over there. But just to give you a little bit of idea what these are, in the previous page we just talk about, like, there are different ways of determining or defining the uncertainty, right? And especially here, if you had multiple measurement, there's one way of defining it, the uncertainty as the standard deviation, and some people define it as max minus min and half. Similarly, using this mathematical format, the combined uncertainty, some people are more focused on getting the max possible error. And what they do is they're looking for the absolute value of this and adding all those. Or some people find this guy and square it, and they add all those squared values, and then they put a square root over there. So these are just two different ways of defining this combined uncertainty or uncertainty propagation. All right, so let's move on and try some examples here together. And there's this case here where you would like to find out the difference of the height there for some reason. So the height of this little person is obtained like that. It's 120 centimeter plus and minus 2, and this is the uncertainty. And this person's height is 175 plus and minus 1, and that's the uncertainty for that case. And the question here is, what's going to be the uncertainty in the height difference? So we can just call this h is h2 minus h1. What do you think the delta h is going to be? In the previous case here, we were adding these two values, and the uncertainty, we just added them, right? So in this case, we're subtracting, so the uncertainty, maybe we subtract it? Probably not. That's the reason why I'm asking, maybe, right? Let's try to find that thing. So we can try the similar approach. We can find the minimum case. And what would be the minimum case here? I would like to find the min value of this guy and the max value of that guy, wouldn't it? So the minimum value is 174 for the height of this person, and the max for that one is going to be 122, given this uncertainty. And we're subtracting that, and that should give us 52. And the max we can get from this difference is what? This one I have the max value, and this one I have the min value. We can have the max value of this is 58, right? Then from here we can think h is going to be around, like, the center value here is 55 plus and minus 3 centimeter. Yes.
Why is it 174?
The question was, why isn't this going to be 174 minus 118? And the reason why is I want to find the case where it makes the h value to be the minimum. So we can think this guy has a height ranging like that, and this has a height ranging like that. So I want to find a case where the height difference is minimum versus the height difference is the maximum. Does that make sense?
Yeah.
Yeah. So those are these two cases, and we got this. So we can see that delta H was the sum of H1 and sum of H2. And we can try following the definitions we had in the previous case, the absolute and the most probable error. let me just copy this guy down here so that it's easy to reference. So the absolute value we would like to find out is delta H1 delta H times H1 plus the second variable delta H2 delta H times delta H2. And from here we can have delta H1 delta, and what's this H? This H was H2 minus H1, so it's H2 minus H1. And don't forget about that delta H1, like that. And we also have this delta H2 delta H2 minus H1 times delta H2. So all I did was apply the actual values into this formula, which gave us something like that, and instead of the H, I provided this in there. And so in this case, what do we have? Anyone? It's -1, isn't it? You can think this as like delta x over x, 2 minus x, something like that. And so in this case, it's going to be -1. So we have -1 times delta H1, and we have an absolute value around it. So this -1 basically becomes nothing, right? So it's going to be delta H1. And what about this guy? What do we have for that case? Anyone? We have 1 here, right? This is just a constant, so this versus that, we have 1 times delta H2. We have absolute value, so this is basically a delta H2. And we're adding these two together. So we just got that thing. Okay? And let's try the other case where we're trying to find this RSS, the most probable error. Let me just move this thing down there so that I can take a look as well. Big square root, and inside there we're going to have delta H1, delta H, delta H1 being squared plus delta H2, delta H, delta H2 being squared, like that. Isn't it? It's a little bit of tongue twister, but that's what we have. And actually we got the corresponding values for this one is basically this one, which was -1, right? And this one is this guy, which is 1. So what we have is square root of minus delta H1 being squared plus delta H2 being squared. This is nothing but, if we plug in the numbers, H1 was 2 and H2 was 1, so it's 2 squared plus 1 squared square root. And that gives us something like 2.236 centimeter. So depending on the definition of the uncertainty or the combined uncertainty, the values may be slightly different. And then let's see how we can use this thing to report that thing into the final uncertainty of this combined value. Your uncertainty is reported always. The common practice is that it's reported with 1 or 2 fecund digits. So we had 2.236, and that one has to be either 2.2, 2 digits, or 2, which is more conservative here. And it depends on the application or depends on the field. Some fields want to have more accurate value. They accept 2 digits. Some want to be more conservative about these, and they just accept one significant digit there. And so based on these, depending on those cases, the reported value must be rounded to the same decimal place as the uncertainty. So H is going to be 55.0 plus and minus 2.2 centimeter, or H is going to be 55 plus minus 2 centimeter, like that. Okay. Any questions up to this point?